Okay, so I'll be talking about the enumeration and succinct encoding of AVL trees, which is joint work with Steve Meltzer, Ian Monroe, and Ava Pun. Uh-oh.
Okay, you need to click on the slide with the mouse, and then it will be this one. Okay. Yeah, it's because it's not click once, and then it should work.
Okay, so first I'm going to motivate the idea of doing both a succinct encoding and also enumerating the AVL trees. So we'll start with storing binary trees. And the naive approach, which is probably covered in every first year algorithms course, would just be to store a pointer to each of the children nodes. So here, for example, node 1 is pointing to 2 and 3, and node 2 points to 4 and a null node. And this is a pretty straightforward way of storing binary trees, and it requires O of log n bits for each pointer, because you need to be able to distinguish between all of the n nodes. And there are 2 n pointers, so it requires O of n log n storage in order to store a tree with n nodes. And immediately you might ask, what's the minimum storage required to store a binary tree? So obviously we have to enumerate in order to calculate how many trees there are. So here's the generating function for binary trees. We can use analytic tools to get the enumeration, and we can find out that you need 2n plus little of n bits in order to give every binary tree a unique string. So 2n is much smaller than n log n. So can we achieve this 2n bound, or is it impossible? So if we can achieve the optimal bound, we'll call that a succinct encoding. And that's where we use the information theoretic minimum number of bits to store data structure. And in general, we also want to have some performance guarantees, because you could just write down a list of all the different trees and then just map one to one. But then you wouldn't really be able to do anything with that tree. You would just be able to recover the tree. It would not be very fast, and you wouldn't have any nice properties. So we also, in general, want to have some operations that you can perform efficiently, and you don't want to have to store all the different possible strings mapping to the trees. You want to just have a relatively good algorithm for encoding and decoding the trees. But so here's an idea for succinct encoding of binary trees. The first step is to give every internal node external node, so that each one has exactly 2 children. So here I've done that on the slide. And then the next step is to traverse the tree in level order and write a 1 for internal nodes and a 0 for external nodes. So here we have this bitmap. You can see internal nodes 1 has a 1 in it, and for example 6, which is an external node, has a 0. And it turns out that using pretty straightforward steps, you can traverse the tree. So you could go from a node to its child node or back up to its parent node. And you can add some small number of bits to support even more operations. In general, we might want to know how big is the subtree root at a given node. And adding just little o of n bits, we can support all these additional operations. So in this case, we want to know, is this actually a succinct encoding? So we want to know how many bits do we use here. So we started with n nodes. We added n plus 1 additional nodes, and we used 1 bit per node in the new tree. So we used 2n plus 1 bits. So this is a succinct encoding. But what if we care about more than just the storage costs? Because in general, binary trees can be very inefficient. A random binary tree on n nodes has average depth square root n. And that means you have to, if you want to do a binary search, you might have to do O of n, square root n comparisons in order to find any node in your tree. And although we do have some benefit, which is that the average depth is only O of log n, the worst case could be O of n. So this could be very bad if you have some efficient operations that you want to do. So maybe we could construct a tree that has shorter depth guarantees, and that would be AVL trees. So an AVL tree is a binary tree where the height between 2 nodes differs by at most 1 for every node. The subtree on the left and right the height differs by at most 1. So you can see here, each of these satisfies that requirement. And now we could ask, okay, we have a succinct encoding for binary trees. Is this encoding still succinct if we just try and use it for the subclass of binary trees, which is AVL trees? So Adelson, Velsky, and Landon.
There are two, not three.
Yes, Velsky, Landon, I think. Or Adelson. Yeah. Okay, so we're going to enumerate the AVL trees. So we have symbolic class. Here we go, this standard model. And here you've got, we can construct a tree of height h plus 2 by taking a tree of height h plus 1 and combining it with either a tree of height h plus 1 or a tree of height h. And then this little coefficient of 2 here comes from the fact that we could put the shorter tree on the left, or we could put the shorter tree on the right. And then if we take the union over all the different possible heights, then that gives us the class of all AVL trees. And then we can compute generating functions given this symbolic expression. And then our generating function is just the sum over all the different heights. And now we run into a problem because we don't have an obvious way to get a closed form expression for our generating function. And also, we're recursing on the height, but we're actually enumerating on the size of the trees. And so that presents an additional problem. But fear not, because we can perform singularity analysis on A of z in order to calculate what is the singularity of smallest modulus, and that will give us the exponential growth. So the first question we'll ask is, when does the generating function diverge? And we'll start by finding the fixed point for our recurrence, which gives you 1/3. And then it's easy to see that if a sub h of z and a sub h plus 1 of z are both greater than the third, then h plus 2 will be greater than the third. And you'll have an infinite sum of a bunch of values that are at least 1/3. So this will clearly diverge. And the next question we'll ask is, when does A of z converge? So we're going to define this new parameter alpha of h, which is going to be the unique positive solution to AH of z equals 1/3. So this will be the value of z that gives you that fixed point for a given height. And here I've plotted the values for alpha h going up to 10. And you'll see I've put the odd values in blue and the even ones in red. And if you look at them, it looks like one of them is a sequence that converges downward, is strictly decreasing, and the other is strictly increasing, and they seem to converge to the same limit. So that gives us some hope that we might be able to say something about these alphas. And in fact, our first lemma is that there is a limit as alpha goes to infinity, as h goes to infinity, and it's equal to the value starting with 0.5219. So our first lemma is that this limit exists, and here's the way that we get there. We start by showing that alpha h is strictly decreasing for the odd h and increasing for the even h, as I showed on the picture in the slide before. And then we'll show that the odd values are greater than the previous even value. And lastly, we'll show that the odd and even limits both converge to the same value. So 1 and 2 show that the upper and lower limits exist, and then we just have to show that those two limits converge to the same value. So once we've shown that this alpha exists, now we have an additional tool to look at to do the singularity analysis. And our next lemma shows that A of z converges inside the disk when the magnitude of z is less than alpha. It's actually pretty straightforward to show this once we've already computed the limit alpha just by plugging in smaller values of alpha and showing that eventually you have the a sub h is less than one, both less than an h plus 1, less than 1/3, and then ultimately you see that it goes to 0 very quickly, geometrically, in fact, so that the total summation will converge. And similarly, we know that whenever z is greater than alpha, it will diverge because we'll eventually get two values where a sub h plus 1 and a sub h are both greater than 1/3, and as we showed before, that causes A to diverge. So now our theorem says that if the exponential growth is alpha inverse, and theta, there's some sub-exponential component theta of n, and here's the proof. It's very straightforward. We use the previous lemmas to show that alpha is the singularity of smallest modulus, and then we can immediately conclude that 1 over alpha is the exponential growth. Yes?
You know what alpha is?
So alpha is a transcendental number that starts with 0.5219, and you can calculate it to arbitrary precision by calculating the a sub h term and then solving to find that a sub h equals 1/3. That's a good question. I think there are results somewhere in analytic combinatorics that show that you can't have this sort of behavior unless it's transcendental, but I don't remember all the details of the argument. Okay. Okay. In any event, you could just take my word for it that it's transcendental, and offline I could tell you maybe the details of that. So here we have the exponential growth, and now we don't want to just stop at AVL trees. We thought maybe we could come up with another similar class of trees, and then we could enumerate those trees. So our first thing was, okay, maybe we'll do left-leaning AVL trees. And a left-leaning AVL tree is just a regular AVL tree, but instead of the smaller tree could be on the left or the right, we insist that the smaller tree is on the right. And all that does is change that 2 that I mentioned earlier into a 1, but we would have to redo the entire analysis that we did for AVL trees. So we figured, forget that, we'll just come up with a general expression, and then we'll never have to do the analysis ever again. And it turns out, as long as you have this union of generating functions which partition some counting sequence into different groups, and you have this recursive formula with some function f, so that they depend on some constant number of the previous terms, then if they behave nicely, we can conclude that there is a limit beta, which is analogous to the alpha in the previous computations. That limit will exist, and the exponential growth will be proportional to 1 over beta. So now that we've got our enumeration, we can go back to our encoding of AVL trees. And we'll start by using the enumeration result to see, was our original encoding succinct? And as you might have guessed, we only need a little bit less than 1 bit per node for AVL trees, and we were using 2 bits per node before, so we don't have a succinct encoding. But maybe we can improve on our 2n plus 1 bits that we use in our general tree and come up with something that works for AVL trees. So here's our encoding algorithm. We start with a large AVL tree, and we identify this subtree tau, where, loosely speaking, every node in our subtree tau is the parent of a large subtree. And I'll say the large subtree is a subtree that has size that's on the order of log n, but I didn't want to draw a tree with like 300 nodes. So here I've sort of fudged it a little bit. So they have only, I guess large in this picture is 5 or 6 nodes. And then the next step will be to identify the leaves of this tree tau, and we're going to name the shapes of the subtrees that are rooted at a leaf of this tree tau. So what I mean by that is we're going to just enumerate them all and write a string for each one. And because they're roughly, we know that all the subtrees are relatively small because otherwise the children of these leaves would also be in the tree tau. And so since they're small, we can count up how many there are, and there are little o of n possible shapes for these blue-rooted subtrees. And so we can just write down a table that lists all of them, and then we can just map each one so we can use the minimum number of bits while still preserving our desire to have an efficient encoding and decoding algorithm. And then we're just going to write down tau, which is our tree in red, plus blue. Then we're going to write our code word mapping so that if you see, for example, the string 0, 0, we know that that refers to the tree with this shape. And then we'll write down the names of the trees using the code words in the order of the leaves. So first we write down, say, this one's name, and then this one's name, this one. We might actually start with this one since this will be first in the level order mapping. But we just go through and list them all and write them sequentially, and we'll be able to use our properties from before. One of the operations that you can do in a succinct encoding on a binary tree with the general encoding is to write down, is to get the index of a tree in level or of a leaf in level order. That can still be done efficiently without adding too many extra bits. So now, just to summarize what our algorithm is, we start with subtree tau, and we can write that down using our regular succinct encoding because it's a small subtree. Then we'll write down the leaves of tau, which are the roots. We'll write down the subtrees, the shapes of the subtrees. And then we'll store tau, the lookup table, and the code words in order. So why does this encoding work? Well, the lookup table will have little o of n because we know that there are not very many distinct shapes. The tree tau has size little o of n because there can't be too many nodes in an AVL tree which have which are the parents of a large subtree. And then finally, the names of the code words are asymptotically optimal because the number of AVL, all the subtrees are also AVL trees. And since we're just using the minimum number of bits to write down the shapes, because we're just enumerating them all, we know that the code words will also be asymptotically optimal. And then, of course, we don't want to just stick with our encoding for AVL trees. Maybe we want left-leaning AVL trees or some other balanced shape. So we'll just come up with a general encoding that works for any weakly tame class of trees. So this is following from a previous work where they show for a tame class of trees, which has a few extra conditions on these three conditions here, but we were able to delete one of the conditions and make one of the conditions a little bit weaker. So we call it a weakly tame tree. And I guess we show that the subtree, that if a class of trees satisfies these properties, then there exists a static succinct encoding for one of these trees. And I use the word static because although you can encode and decode somewhat efficiently in the number of nodes, if you want to insert a node or delete a node, you would have to basically throw away the tree and start over from scratch. And so that might not be very efficient in terms of compared to, say, when you're actually using an AVL tree, one of the benefits is that you can insert and delete efficiently. So unfortunately, we can't preserve that property, but we still, if you have we still preserve, obviously, the balance condition for the AVL trees. So in conclusion, we have the first theorem showed that we can enumerate all kinds of balanced classes of trees or other combinatorial structures as long as they satisfy this particular recursive structure. And we have improved from static succinct encoding on tame trees to any weakly tame class of trees. So there might be some other classes which also fit into our new category. And lastly, I just want to talk about some future directions that this work could go in. So one thing you might want to do is construct a dynamic succinct encoding. And I believe there is a dynamic succinct encoding for general AVL tree, or for general binary trees. I don't know all the details of that, but it would be nice to construct this more specialized encoding where you can be succinct for some subclass of binary trees. And then the other thing we might want to do is apply our enumeration tools to balanced data structures beyond AVL trees, or maybe even beyond trees. Any recursively defined combinatorial structure could work with our encoding. And lastly, we might want to improve from just getting the exponential growth to getting even more information about the sequence. So thank you.
Thanks a lot. Are there any questions?
So, AVL tree, if I remember, a precursor of 2-3 trees. Jan probably knows it better. And there is an old analysis by Andrew Odlyzko about 2 or 3 trees. How the things are related?
So actually, the original paper you mentioned with 2-3 trees suggests the constant that we have, but there's no proof given for how that constant for the exponential growth is derived. 2-3 trees.
I think Andrew Odlyzko had a good proof, but I don't know whether that is the same constant.
Oh, no.
No.
It was never published. The paper says this is the result, the proof is coming up. Never happened.
Really? Okay.
Yeah.
We contacted.
Yeah.
On Andrew Odlyzko about, in fact, joining us in this, and he had not published it, and he chose not to. So.
Anyhow, very nice stuff. Very nice thing.
Yeah, I
Thank
contacted him about 30 years ago on that.
Oh, so you were ahead of us in the queue, and he hadn't done with you yet.
But anyways, one last note on the 2-3 trees. There's a slight difference, which is that all of the subtrees have the same height in the 2-3 tree. And so because you don't have those dependency on 2 different heights, the analysis actually becomes a lot easier.
Conrado has a question.
So one question is not related to analysis, and the other one is, the first is, your Succinct representation is not dynamic, but can you use it to navigate in the tree?
Yes, so
Okay.
I didn't mention the details. The details are somewhat technical, but we support all the same. So in general, with succinct encodings for binary trees, there's a list of operations that you want to support. And in the literature and in the extended abstract, you can see the list that we've written it down, and we support all those operations efficiently, which means using, I think, log n bit RAM model and constant time.
And the other one is, do you have any intuition about the sub-exponential behavior of that?
So our method doesn't.
Yeah, I know. you
Yeah,
have
right.
it.
Our method doesn't really give any intuition. I think in the original paper by Odlyzko, he does say something actually about the sub-exponential growth. And if you look for 2-3 trees, there is actually a lot more details about the sub-exponential growth. There's something where there's a periodic nature to it. And so that periodic is somewhat difficult to extract.
Yeah, Jim?
So I wasn't clear when you mentioned dynamic succinct encodings on your, I think it was your last slide
Yes.
before this. Can you do that, do you think, for all weakly tame trees?
So I'm not exactly sure how you would improve, how you'd take our version and make it dynamic. I recall the details where for general binary trees, a dynamic succinct encoding that the technical details are quite specific, and so I'm not sure that it would necessarily be applicable in our setting. But it's, I think, possible that you might be able to still get dynamic encoding.
And a related question to that is, do you think that there are classes of trees where it's possible to get static succinct encodings, but not get dynamic succinct encodings?
That's a great question. I optimistically want to say that anytime you can get the succinct encoding, you get a dynamic one, but pessimistically, that probably isn't true.
Yep.
I just want to comment, that that's a great picture of an AVL tree that you have there. Love, a little bit off balance here and there, but.
I
Good picture.
because we're in Bath, I tried to get an English oak tree. I don't know if anything about trees, but the internet suggests that this might be an English oak. So for the purpose of our
I have a question
setting
here.
So thanks. Actually, thinking about this tree, do you think that almost all biological trees are perfectly balanced? I mean, you're not specialist, I know, but this one looks like.
I think no, they're not, because they tend to. My intuition says they tend to favor like growing towards the sunlight, and so if the sun is in a certain, shines more brightly on one side of the tree, that might thrive more.
On that note, I suggest we thank Jeremy for the great talk. Thanks.